thank you very much for the invitation. Even though I didn't know what the Stockholm, wow, that's a difficult long word. I didn't know about you until I was invited, but I was really excited. And I'm really excited because I think the most wonderful thing about research is actually not about the things we discover that no one knew before. What really drives me is the opportunity to meet a lot of people and travel around the world to discuss things that we find equally fascinating. And I will speak a little bit from my own perspective, but very much I feel that I'm here representing the whole cardiac MR group in Lund. And so I would like to start with actually just showing you the names of the people in the group, because if I were to actually put up photos, it would be very crowded. And if you see some names that are bolded, it's because these are our engineers and physicists and mathematicians. Because even though it's a part of the medical faculty at Lund University and we do research on heart patients, we wouldn't be where we are and we wouldn't be able to do what we do if we didn't have this really close collaboration with engineers. So we have engineers and they need to understand physiology, and we as physiologists need to understand a bit about engineering and the basic understanding of you can actually program a computer to do the things that I would otherwise do manually. And that saves us a lot of time, and it helps us develop tools to develop new ways of understanding how the heart works. And I understand that you are all from different backgrounds, and I'm just assuming that some of you are more towards the engineering side. I hope that this presentation will give both those more towards medicine something to be inspired by, but also if you're doing maths or any kind of engineering or programming, this is the thing for you to go into medicine, to help medicine become even better at diagnosing and treating patients. So I'm going to start from the very beginning to tell you about some common misconceptions in cardiac pumping. So to the left here, you have an animation taken from Wikipedia, from the article about the heart that illustrates cardiac pumping. And to the right, you have a textbook it's called Vander's Physiology, and it's the textbook we use for med students in Lund, for example, to learn cardiovascular physiology. And if you look carefully, you can see at the Wikipedia animation, for example, you can see how the heart contracts with a squeezing motion. And I guess if I was to ask you guys, show me with your hand how the heart pumps, you would all go a bit like this and just open and close in your hand, because that's how we usually think that the heart pumps. And also, if you look at the image, you can see that the valves, so that's the plane separating the atrium from the ventricle, they are completely still. And it's actually the rest of the heart moving up and down. So this is what most people think it looks like. And it's not just people not trained in medicine. This is what thoracic surgeons and cardiologists think the heart looks like when it pumps. So this is how the heart really works. Here is a cardiac MR image of the heart. You have the black around the heart are the lungs. And in the center, you have what we call a 4-chamber view of the heart. And if I use my pointer, can you see that then? So here you have the left ventricle. The left ventricle delivers the blood to the body. And then you have the right ventricle pumping blood to the lungs to get oxygenated. So as blood comes back low on oxygen from the body, it enters the right atrium and goes through the valves down into the right ventricle. And from there, it's pumped to the lungs. Then it returns to the left atrium, goes through the valves to the left ventricle, and then it's ejected. So how does the heart do this? Well, people think they know. They think that it's sort of the heart squeezes, and therefore you get the blood ejected. But if you look at this cardiac MR image, and look at the outer boundaries, you can see that the outside of the heart is more or less completely still. There is very little volume change between when the heart fills and when it ejects blood. The heart volume variation is actually just 5%. Instead, what happens when the heart pumps is that the valve plane that was shown to be completely still in the first slide actually moves up and down. So the heart pumps like a piston pump. So if there's one thing you should remember leaving this talk today, is that the heart pumps like a bicycle pumps. So it pumps with the valves going up and down, and that is what delivers the stroke volume into the body, and it's not a squeezing motion. And this is more or less the foundation of a lot of research that we do in our group, because if we can't understand this normal basic pumping mechanics of the heart, how can we then understand when something has gone wrong? So we are very interested in trying to just understand what is normal, how does normal work, what does it look like, and try to measure that. So what can we do using magnetic resonance imaging? So this is a scanner, and it's actually just by chance the one that dedicated cardiac scanner that we have in the hospital. We have access to 2 different scanners, one dedicated only for heart patients that we just got, and then we have another one that we share with radiology. And using the MR, we can get a lot of information about the heart. We have anatomy and function. So here on the top left, you see a 4-chamber view. You recognize it from the last slide. You have the left ventricle, the right ventricle, left atria, right atria. And then on your top right, you have something we call a 3-chamber view. And that's because we can see 3 chambers. We can see the left ventricle and the atria. And then sort of hidden behind the left ventricle, we see the right ventricle, because in this image, we have rotated our slice positioning 60 degrees so we can image another part of the heart. So bottom left is another 60-degree turn, and that gives us a 2-chamber view showing only the left ventricle and its atrium. And then we have the short axis slice. And if you think of a loaf of bread and then you slice it in many slices, and then you just take one slice of bread and you look at it, that's what you have in front of you here. And all these can also be played as what we call sina, which is when we take a whole heartbeat, or actually take several heartbeats, and then we just what do you call it? Average them into one heartbeat to get good quality. And then when we play them like this, we can also study the function. So if you, for example, have had a heart attack or myocardial infarction, you get an injury to the muscle of the heart, and that part of the muscle will not be able to contract fully anymore. So looking at these images, we will be able to see if there is a decreased contraction in any part of the ventricle, giving us an idea about a problem with cardiac pumping. Another common thing we use MR for is to visualize a myocardial infarction. So that we do using contrast agent. So you give your patient contrast, and then you take images like this one. And what you can see between the 2 arrows is a very white line, which is a white line where the myocardium, the muscle wall that should be black, is instead white. And that shows that we have either edema, so that is increased water content, or fibrosis, if it's an old infarction. So this is a really important way to both diagnose, but also if we want to follow treatment in research. If we want to see if a certain treatment for acute myocardial infarction is working or not, you would, for example, you would randomize the patients coming into the ER with different treatments, and then look at their MR scans afterwards and see, did anyone get a decreased infarct size due to our treatment? And that would sort of be the outcome telling us which treatment was the best. So these are very well-established tools that we have, and there are many more. And then there are tools for the future that are more or less already here. And the ones I will talk about today are MR during physical exercise. And the second one is visualization and quantification of blood flow and kinetic energy in blood flow. So this slide shows exercise CMR. And to the left, you have the picture from the company selling the ergometer we're using, and to the right you have a photo of my colleague Fabian from Hamburg, who was really keen to try the ergometer when he came to visit us in Lund. So this is what it looks like in the patient waiting area close to one of our scanners. So I would like to just stop here and share a little story about exercise CMR and how it all started. Because it started approximately 9 or 10 years ago when I was done with my PhD and I was going on my postdoc. And the professor that I was going to work with, his name is Bengt Saltin, and he is a world-renowned exercise physiologist. A lot of the things we know about how exercise affects our body has come from research that he and his colleagues have done. And he was really curious about the things that we could do using MR, because that was not a method that he was familiar with. And he asked me, can we do exercise inside the MR scanner so we can study the heart during exercise? And I said, no, that's not possible. Because as you know, who have all tried to take a photo at some point in your life, you know that in order to get a good photo of something, the object needs to be very still. Or you have to have a really fast imaging technique. And when it comes to cardiac MR, you have a beating heart, so that's constantly moving. And we solve that by using ECG. So we're matching the electrical activity of the heart with the imaging sequence to sort of get the heart to be still when we take the image. Also, we ask the patients to hold their breath so we don't have the problem with the respiratory motions. So we can overcome that during normal imaging, but during exercise, it's really hard to hold your breath because you're short of breath, you're exercising, you have a really high heart rate, and also you're not still, you're physically moving while you're exercising. So I said that is not possible. And Bengt said, okay, let's do it anyway. And I think he was like 76, 77 years old at the time. And he did not, I mean, he had done so many things. So no was like, it was not an option. So he invented an ergometer that was MR compatible because it's a big magnet, so you can't bring any metal objects into it. So it was made of plastic and wood. He designed it. And then his friend Fleming, who used to build, rocket engines for the space shuttles. He constructed the ergometer. So 3 years later, after I had said, this is not possible, and the professor of clinical physiology who took sort of cardiac MR to Sweden said it's not possible, we were the first ones to publish on cardiac pumping during exercise inside the MR scanner. So what this story really taught me was that in research, the limits that you see today may not be limiting tomorrow. So don't limit your visions on what research you want to do to what methods are available for you today, because you have no clue what you will be able to do in 10 years. So if you have a vision, stick to that vision, and maybe you will be the one developing the technologies to make it possible, or maybe someone else with a similar dream will do that for you, and then you can use it. So exercise CMR is something that I keep coming back to in terms of dream big and go for it, because what I know today is not the same thing that I will know in 10 years. And maybe I can do what I want to do in 10 years. So just go for it. That's a take-home message. So we do exercise more. We also use something called 4-dimensional flow. So 4-dimension refers to the 3 dimensions plus time. So time is the 4th dimension. And doing 4D flow and adding, like we've done here, streamlines, we can visualize how the blood flows inside the heart. So for example, in this paper, we saw that on the right side of the heart, the blood goes from the atrium into the ventricle in sort of a helical spiral flow. And you can also see on the image to the right, you can really see that spiral in the right atrium. And that, we believe, is a really clever way of the heart to just keep energy, the kinetic energy in the blood. Because if blood was to enter the heart and then stop, and then have to accelerate again when it goes into the ventricle, and then stop, and then have to be accelerated again to go out to the lungs, or for the left side, go to the body, that would require a lot more energy compared to the way it seems to work, that actually blood comes into the heart and just keeps on moving in these swirly flows from the atrium to the ventricle and then flows out in the aorta. And this is some things that we didn't know until we could visualize it. And we can also do this in this moving image like this. So here you can see we've coded the velocity. So red indicates high velocity and blue is lower or no velocity at all. So when the blood, the streamlines turn red, is the ejection phase of the ventricles. So you have the blood going out through the aorta or the pulmonary artery. And so that's where it goes. And then here we have the filling of the ventricle. And then we have the late filling coming here and then ejection. So here we get a sense of the speed. And since we have the mass of the blood as well, we can measure that. We can calculate the kinetic energy in the blood. So in this slide, you have on the top, you have systole, that's the ejection phase of the ventricle. So that's where you can see that we have a lot of red in the aorta during systole. And that is because we accelerate a lot of blood, so high velocity and a high mass through the aorta. So that's why it becomes very red. And to the top right shows the RVOT. So that's the outflow tract for the right ventricle. Same thing, a lot of blood being ejected through the outflow tract. The middle panels show the early filling, where you can see that we have a red area, center of the left ventricle, showing a lot of kinetic energy. And then bottom panel is the late filling, the last filling of the ventricle, where the kinetic energy is a little lower because the mass of the blood is a little less. Using 4D flow, we can also put something called Lagrangian coherent structures. And maybe some of you are familiar with what that is. So you may laugh at my explanation now, and that's okay. But basically what they do is that they separate flow coming from one place from flow coming from another place. So in these images we have, I will soon play you a video, and you will have blood coming from the atria into the ventricle, and that will the structures will then separate from the blood that was already in the ventricle. So here blood comes in, and you can see that it forms a vortex that fills the whole ventricle. So to the left, you have a healthy heart. So this is what it should look like if you're healthy. To the right, you have a patient with heart failure where the ventricle is dilated. So the blood comes in, but instead of filling the whole ventricle, it sort of slides down close to the wall. And what does that mean? Well, we don't know. So this is, now we can visualize it, and we can quantify the energy, and we can study it. Will it have any implications in the future in how we treat patients? We don't know. but maybe. So this is a very first step to understand more about how the heart works. Because everything that we do in our research group can sort of be summarized in this why. Why are we doing what we do? Because we need to understand how the normal heart works to better diagnose and treat a heart when it doesn't work. So to get here, to reach this why, we have several research lines. So in our group, we have PIs working with heart failure, acute ischemic heart disease, congenital heart disease, fetal MRI, and pulmonary arterial hypertension. And then we have normal physiology and exercise physiology. And of these research lines, I am the PI for heart failure, normal physiology, and exercise physiology. And that may seem like I'm 50% of the research group, which I'm really not. But everything that we do ties together. So even though I'm at heart failure, my colleague Henrik, who is for acute ischemic heart disease, his patients will eventually get heart failure, meaning that he's also a PI of heart failure. So we try to always work together to find synergies between our research lines, so that if I acquire data from 25 patients, it should not just be for one research paper. That data is really valuable and it should be able to be used in many research lines. So I don't only acquire images that I need, I ask my colleagues, what kind of images do you need? And maybe someone says, I need 4D flow. And I say, okay, so I'll add the 4D flow. Someone needs contrast, so I will add contrast. And we try to communicate all the time to make the most of what we have. So I will continue now with some examples from my own research. And I think of what I do as very closely connected. So if you look at it like this, there's a triangle where I put normal physiology and heart failure at the base, and they sort of connect at the top in exercise physiology. And this is because I use exercise and exercise physiology as my way of stressing the systems. So I want to see, so that's the extreme part of how does the heart adapt to extreme situations. Well, exercise is an extreme situation, or can be. So I use that to stress normal physiology to see how it adapts. And also I stress heart failure to see how heart failure patients adapt to exercise. And that helped me understand more about the physiology. And I think this is also, when doing research and finding your own research career, it's very much about finding what's unique about you. What do you know, or what are you inspired by that makes you unique, so that you can do research that is unique. And I'm a physiotherapist. I started as a sports physiotherapist working in sports medicine, treating knee injuries or telling people how to take care of their shoulders. So exercise is really the core of what I know. And my fellow colleagues who are medical doctors don't know exercise physiology. So I can add something to our research that makes me unique. And it all started actually with this. This is my very, very first research paper. And it's also one of the most important ones that I've ever published, because it really puts normal physiology and exercise physiology together. So here you have 4 hearts. To the left, you have a female control. So she's untrained. It's actually me. And then you have a male control, also untrained. And then we have a female elite triathlete. And then we have a male triathlete. And the white line in each image is just for your reference, so that you can see that I have not zoomed in more on the male triathlete to make his heart volume larger. This is actually the true difference between the size. So female control, if you would measure the ventricles and the atria, just the total volume of that would be around 600 milliliters. That's pretty normal for an untrained woman. And then the male control, he's about 800. And the female triathlete is just under 1,000 milliliters. And the male triathlete is about 1,100. So this shows how exercise affects the size of the heart. So just look at the controls. Starting untrained, not having influenced the system, men usually have larger heart volumes than women because it correlates to body size. So women are generally smaller and therefore have smaller hearts. And that can be changed through exercise. So the female triathlete and the male control are actually, they're the same height, but she has a lower weight. So she is physically smaller than the male control, but her heart volume is still larger. And that is due to the amount of exercise that she has done in her life. So what we did in this study was to have everyone do an exercise test to see their maximal exercise capacity. That's VO2 max on the y-axis. And then we measured their total heart volume. So that is left and right ventricle plus left and right atria. And then we just plotted everyone who was in the study. And if you look at small heart volume and low oxygen uptake, open triangles, that's our control group, men and women. That's where they end up. And then filled triangles, it's a bit hard to see, but that's sort of the next group on the line. That's the handball players. And handball players, elite handball players, they don't do a lot of endurance. So no surprise that they weren't very fit. And then we had the soccer players in the filled squares, and then the triathletes, the most fit endurance athletes, had the largest heart volumes and also the highest oxygen uptake. And then we have sort of an outlier, which is this triangle here, which is a handball player who qualified almost as a triathlete. And that was because he just really, really loved running. So when he wasn't playing handball, he was just out running just for fun. So that's why he stands out. So this gave us a really good understanding of normal physiology, how the heart volume relates to exercise capacity. And VO2 max is one of the measurements that we use when we decide whether or not a patient needs a heart transplantation. So it's an important measure also in the clinic. So we thought maybe we can use this to be better at understanding heart failure. So we did another study and added patients with heart failure. And here you can see what's new are the open circles called patients. These are patients with heart failure where the heart has started to dilate and just blow up like a balloon. So it's bigger and bigger. Like athletes have big hearts, heart failure patients have big hearts. The difference is that the athlete's heart is really good at pumping blood and the heart failure patient's heart is really poor at pumping blood. So this gave us the idea of actually creating an index. So if we divide the oxygen uptake with the total heart volume, I don't have that slide here, but we can actually, with a cutoff value, see if someone is more towards heart failure than normal. And we are working on follow-up studies now to just see if we can use this as a novel measure of early diagnosis of heart failure. Because one problem that we have is if people exercise, which is a really good thing, and have a good oxygen uptake, and then start to become worse, and we just look at their exercise capacity, the VO2 peak, it sometimes looks like they're normal, they're healthy, but they're not healthy compared to their heart size. If they have a size of the heart which is 1,000 milliliters, they should really have a really, really good exercise capacity. And if they're only okay, maybe they're sort of going into heart failure, but we just can't see it yet with our ordinary measures. But this one is more sensitive to that. So this is future work as well. and I think these studies really show the core of what we do, trying to take 3 research lines, normal physiology, exercise physiology, and heart failure, and put them together to increase our understanding. A final study about heart failure is something that is going on right now, except that there is a pandemic going on right now, so we can't really do this research right now. But we know that physical exercise works as a treatment for patients with heart failure. And actually, it is the only treatment that works if you have heart failure with what we call preserved ejection fraction. That is when the heart has problem filling with blood. So it can pump really well, but it can't fill. And if you don't fill, there is no blood volume to pump. And there is today no pharmacological treatment for heart failure with preserved ejection fraction. But if you have them exercise regularly, they improve. We see that they have improved exercise capacity. We see that they improve in their health-related quality of life. Problem is, we don't know why. And generally, as long as we don't understand why a treatment works, medical doctors are a bit more reluctant in prescribing it. So from a physiotherapist point of view, we can sometimes be frustrated saying, why don't you tell people to exercise? It's really good for them. But if you can't really explain what happens, it's hard to have the right dosage, and we have to be really specific about exercise the same way as we are specific when prescribing drugs. So we're doing research on this, and this research is based on the Fick equation. The Fick equation shows that the oxygen uptake, VO2, is dependent on the stroke volume from the heart, your heart rate, the amount of hemoglobin you have in your blood, and the AV difference. So that's the difference between how much oxygen you have on the atrial side, and then how much oxygen is left on the venous side, because that tells us how much oxygen was consumed by the mitochondria. So basically, this means that stroke volume and heart rate, that is related to the heart. Hemoglobin is a part of your blood, and the AV difference tells us about what happens in the muscles and in the mitochondria. And previous research has either looked at the heart or looked at the muscles. And what they all have done is to look at how are the patients doing at rest. But the patients have their symptoms during exercise, and they feel they improve during exercise if they have been treated with exercise. So I guess you can guess what I think they should do. They should do cardiac MR during exercise. So in our research project, we will have our patients exercise inside the scanner to look at their heart function. They will exercise on a bike so we can have a true VO2 max objective measurements of their exercise capacity. And then they will perform group training with our experienced physios in the hospital. And they will do this. So they will do baseline examinations with MR, muscle biopsies, and we will look at the mitochondria. We will do metabolomics to really pin down what is going on in the muscles and the mitochondria. We will do all kinds of cool stuff with the MR to get as much information as possible. And we can get a lot of information from these curves with the gas exchange as well, telling us about the metabolism going on while they're exercising. And then they will answer some questionnaires about health-related quality of life. Basically, how are you doing? And this research will perhaps not be about adding years to the patient's lives, but to add life to the remaining years. Because exercise it's not a curing treatment, but it's a treatment that makes them feel better, be more active in their everyday life. And if you only have 5 years to live, you want to have a good life during these 5 years, and exercise can help you do that. That research has shown, but we don't understand why. So that is why we're doing our research. So I can't stop talking without also getting to just say something about my astronauts, because this is something that I've been working really hard to get in place for a very long time. And that is a collaboration and a research grant from NASA to study astronauts. And that I will do together with Benjamin Levine at Southwestern in the US. He's the one holding the grant. Because a problem that we have with the astronauts is that there are increased cardiovascular risk with spaceflight. We have seen that they have an increased risk for atrial fibrillation. So that is when you have rhythm disturbances in your heart. And that can cause the blood to form blood clots that could be sent to your brain or to your coronaries. So you could have a stroke or a heart attack. That is not something we want for the astronauts ever, but especially not during a mission. Also, the increased radiation, we worry that they have an increased risk of coronary artery disease. And that is also something we need to look into. So starting this spring, we will study 10 astronauts who are going on a one-year mission. And we have 10 astronauts who will have 6 months missions, and then 10 who will go 3 to 6 months to the International Space Station. And this is a research project that will take at least 10 to 15 years to complete because it's not that often that astronauts actually go into space, and we don't have that many at a time. So it's a long-term project. Ultimately, the goal is to understand more before we go to Mars, which is a 3-year mission at least. And this is sort of this is a project that we just do for fun. And I think that's important too. You need to have research that brings in some money. You need research funding. But then there are also, in academia, sometimes there is time to play. And I would say astronaut research, that is our playtime. That's what we do for fun. My main supervisor was applying to become one of the Swedish astronauts, and he was the 3rd runner-up to go to space. So he's very easy to convince that we should do astronaut research nowadays. So with this, I just want to conclude and say thank you. And I've added here my email address, Twitter account. I tweet physiology mostly, and Instagram if you want to. Instagram is more about writing popular science books. So you can contact me there if you have any questions or any thoughts that you would like to share. Thank you.